How's it going?
It's going.
It's going. Oh, I know I was going to grab it.
We weren't supposed to do the whole flip thing, right?
You were supposed to do everything. Everything.
So now, are we supposed to do the flip thing tonight?
What flip thing?
Yeah.
Oh, no. That's chapter 6 is the next chapter.
Alright, so we got a while.
You got a little bit. Do you guys need a packet of problems, by the way? Do you want me
You did that out on Friday.
This one? Oh, I haven't given a different one on Friday.
I heard you and something in the video.
I wondered why I had an extra one.
Oh,
There you go.
thank you.
You're welcome.
Did that say packet of the video?
All right. The whole time? All right, so let's work on some more problems. So let's just remind ourselves of the formulas that we talked about last time. Or just and there's basically the compound interest formula and the compound discount formula. So remember that when we write a nominal interest rate, that was when we used that I with a superscripted number in parentheses. So the interest rate is typically quoted as a yearly rate. But the fact that it's nominal tells you that you're going to be compounding the interest m times per year. So, but the effective interest rate per period will be that I to the m over, or that IM divided by m. Oops. It's per period. So, like I told you at the beginning of the semester, much of what the information is in this class isn't mathematically difficult. Some of it's a little more interesting than others. But most of it is high school algebra. It's more a reading comprehension thing than anything else. So this is one of your first examples of it that you have to read carefully. You need to make sure that you read the difference between effective interest rate. If you see effective interest rate, that is giving you the rate per period. Versus nominal interest rate means you're going to have to convert it to an effective interest rate per period. So you have to be aware of those things. And then you would have the same thing for your discount rate. So if you have a nominal discount rate, you would have dm, and then you would have to do the same thing. You would need to divide out by the m. So let's look at a particular problem. So let's look, this is number 3.17 in your book, for what I mean. So it's 3.17 on page 49. It's weird. The numbers are in the bottom right-hand corner, or the bottom corners, and I wasn't expecting it to be down there, so I didn't see what page. All right, so in this problem, it asks you, or it tells you that the annual interest rate convertible monthly is 12%. Okay, so there's quite a bit of words that are in that. It says annual interest rate convertible monthly is 12%. All right, so notice that the word effective is not used here. It's used later on in the problem, but it's not used in this statement. So the way that you know in this problem that you're given a nominal rate rather than an effective rate is the word convertible. So convertible is synonymous with compounded. And that's our key word here that's telling us, hey, we've got a quoted nominal rate, not a quoted effective rate. Does that make sense? Okay? So, this tells us, hey, Marshall. This tells us that this 12% is your I-12. Nominal rate, so we're using that superscripted with parentheses notation. This is just a notation, it's not actually a superscript. Okay? We're using the superscripted parentheses notation, tells us that it's a nominal rate rather than an effective rate. And we put 12 in the parentheses because it's convertible monthly. So that's the number of compounding periods per year. Okay? So the problem asks us to find the equivalent annual effective rate. So that is some bad handwriting. Find the equivalent annual effective rate. And this is one of the reasons why I tend to give you more handouts as opposed to me writing problems, is it takes a while to write. I'd rather not have to write a whole bunch of things. All right. So, notice that this 12% again is not your annual effective rate because this is a nominal rate. We're going to divide it into periods, and it's going to get compounded for 12 years. So, we know that there's two ways that we can figure out growth in this case. If we have the annual effective rate, I can take whatever the original principal is and just multiply it by 1 plus I, and that will give us the accumulated value after 1 year of whatever the principal is, if it's an annual effective rate. Since we've got the compound interest, in this other case, if I want to do the same thing, I would need to divide this by 12, make it a monthly rate, and then accumulate that for 12 months. Those two things have to be the same, so it would have to have the accumulated values be the same, so I would have to have my principal times 1 plus the annual effective rate has to be the same thing as the principal times 1 plus I-12 over 12 to the 12, because those have to be equal to each other after a year. Notice I don't really need to know what the principal is because it's going to divide out on both sides, right? So I didn't even really need to write that. So I can get rid of those. And notice now I have a formula that equates annual effective rate with the equivalent nominal rate compounded for the year. So this concept is going to come up when you need to convert from one rate to another. And it doesn't just have to be nominal interest to an annual effective interest. You can do nominal interest to nominal discount, for example. You can do nominal discount to annual effective interest. Okay? So you can do these conversions just by coming back to the same idea, and usually we'll equate it for a year. Making sure that they match up after a year's time, and then you'll have the given one, you can solve for the other, which is exactly what we did here. So there's not really much of a formula to memorize, it's just remember that you're going to equate what the accumulated values would be after a year, and solve for the one you need to. So in this particular problem, we would have the 1 plus I is equal to 1 plus 0.12 over 12 to the 12th. Now you have a formula. Now before you do anything with typing this into your calculator, you should have an idea of whether or not this number should be bigger or smaller than 12. Or 0.12, I guess I should say. Should it be bigger or smaller than 0.12? Bigger. Because why?
Because it's an exponential, you're not just adding 0.01 each time.
Right, you're not just adding a 0.01 each time, you're taking a 0.01, after the next period you're multiplying by another 0.01, you're adding it on, and another 0.01 adding it on each time, right? So this should turn out to be bigger. So if you type this in your calculator, or you get something smaller, you type something in wrong. That was kind of the reason why I wanted to mention that. Just gives you a little bit of a check. You know this should be bigger, right? No matter what you do, it's true in general that if I take the I sub m, that should be less than what the I is, no matter what. Because your compound, as long as your m is bigger than 1, I should say. It's possible that you could be given a 2-year nominal rate or something that would be smaller. But just in general, if you're compounding more than 1 time per year, then it should be the nominal quoted rate should be less than what the annual effective is. And this is what I was mentioning last time with mortgage rates. But the quoted mortgage rate that you get isn't the annual effective rate of your mortgage because it's compounded each month. Same with credit cards. Whatever your credit card interest rate is given to you is not the annual effective rate because again, your credit card interest gets compounded each month. You might pay your credit card off each month, pay the interest. And then you earn, hotel miles, airline miles. Somebody might yes.
So with the answer we get for 3.17, should 3.18 just be double that? Because 3.18 says the same thing, but it's 2 years, so it should be double for.
So we'll set up the formula here in a sec. Yep. So, but it shouldn't be. It should be more than double, I think. Let's see what we'll find out what it is. Okay. So anyway. What did you get for this number? 12.68%? Hey, look at that. That was an answer on there, too. It was letter D. By the way, all your answers to these problems are in the back of the book. Well, at least the actual answer, the letter answers are in the back. All right, so if you were going to do 3.18, like Sam asked about, it says the annual interest rate convertible monthly is 12%. Calculate the equivalent 2-year interest rate. Well, there's a couple of ways that you can think about it. I typically like to think about everything going back to a year. But in this case, it's not too hard to make equivalent to be 12 months to go up to, monthly up to 2 years. You just need to do it for 24 years, right? 24 months. Try again. Say the right word. Okay? So for 3.18, if I do 1 plus I12 over 12 to the 24th, that would give me the accumulated compounding of the nominal rate at 12% over the course of 2 years, right? Agree with that? That would have to equal the 2-year rate, but that's just one period. So for the 2-year rate, you would set this equal to 1 plus, I'm going to call it J, because typically we use the letter I to denote annual effective rate. So I'm just going to use J just to represent the 2-year effective rate. It's a different one. That makes sense. Because usually when we use the letter I, we mean a 1-year rate. This problem's asking for a 2-year rate. So this J is representing the 2-year rate interest. 2-year interest rate. Why did I say that backward? So just to emphasize, this is the 2-year interest rate, not annual effective. Yeah, you're right. Yep. I was going to write that down in a minute, but you're exactly right. So you would, in this, the way we've got this set up, you would set it up similarly. But if you wanted to do this in terms of the annual effective rate, that's exactly right. If I want to get the annual effective, this 1 plus j, your 2-year rate, would have to be divided by a half, because there's a half of a compounding period, and then raised to the 1/2. That would get us back to 1 year's time. So that would be equal to 1 plus I. You're exactly right, we have to do a square root. Because it's for a half of a compounding period. I know it's weird.
I guess E for
The 26.97? Is that what they have in the back of the book too?
yeah.
Yeah, okay, cool, good. Good. So if you use either of these, because this was your original annual effective, if you use the 12.68 or the, to use the 12.68 in the second equation or just solve it directly in this one, you should get the same answer. Both of them should give you, what did you say, E, so 27.
0.269.
Yeah, 26.97%. Either of those formulas would work. Like I said, usually I think about things getting equated to after 1 year. So in general, I wouldn't do it for this problem. Actually, for this problem, I would do it the way I wrote it first, because I know that 24 months is 2 years, so I can get it directly from here. But a lot of times, the way I would set it up, I would have set it up as 1 plus I12 over 12 to the 12th is equal to 1 plus 2j to the 1/2. Because that equates it both to 1 year. 12 months in a year, a half of a 2-year period per year. So I would equate those two. That's how my brain would make the two go together and not have to memorize different formulas for different things. Does that make sense? Gracie, do you have a question? I'm multiplying it by 2 because I'm dividing it by a half. Because there's a half of a compounding period, in a year. It's a 2-year interest rate, so you're going to compound every 2 years. So there's a half of a period for 1 year. So I'm setting it.
So it's like if you were doing like 6 months for a yearly rate.
So we can do this not just for, like I mentioned, for nominal rates to annual effectives. You can convert from one to the other, and you can involve discount rates too. So let's look at 3.29. This is on page 51. 3.29 says we've got a nominal rate, a nominal interest rate of 14% compounded monthly. We want the equivalent discount rate, equivalent nominal discount rate compounded or convertible, doesn't matter, quarterly. So again, I want to think about this as accumulated value for a year and equate the two ideas. Okay? So if I was doing the accumulated value for a year with a nominal interest rate of 14% compounded monthly, what would the formula look like? So I was just doing this first part. What would the formula look like? For 1 year. Apparently it would look quiet.
1 plus
1, 4, okay. Divided by 12 to the 12th power, right? That would be the value of $1 after 1 year, right? Or it's an accumulation factor, essentially, right? We just need to multiply by what the original principal was if we were looking for an accumulated value, right? Okay. So that would be this is the amount that $1 would grow to over the course of a year, under a nominal interest rate of 14% compounded monthly. Are we okay with that expression? All right. We want this to have an equivalent nominal discount rate compounded quarterly. But let's remember what we had to have for discount rates. Remember, when we do discount rates, they're computed off the accumulated value and subtracted back down to the present value, right? In general, we would have your present value is equal to your accumulated value time whatever t of 1 minus dm over m to the t, right? Where t is number of periods, right? But notice this expression gives you present value, not future value, right? This is a future value. So if I'm going to set these two things equal to each other, what do I need to do with this expression? I need to divide it over, right? We agree? I need to move that to the other side. So my exponent is going to become negative in this case. And then also in this case, what are m and t both need to be what? They need to be the same because we're doing it for 1 year, and then specifically for this problem, what should m be? Yeah, it should be 4 because of the quarterly, right? So the right-hand side of this equation should be 1 minus dm over m to the negative, oops, just said 4 and wrote m. d4 over 4 to the negative 4.
Does that make sense? Yeah, thanks.
Kind of a sidetrack question.
What?
Sidetrack.
Oh, yeah.
You said sad something.
Sad question. I got a sad question. I got a sad question.
So since the 4 and the 4 and the 12 are the same number, back to that, what we were doing at the very top of the screen, 1 plus 2. Since you divided by 1 over 2 and the exponent was 1 over 2, are those always going to be the same?
If you're equating it for a year, yes. If you're equating to the same, if you're equating it for 1 year to get the equivalent rate, then yes, those will always be the same.
I'm talking like when you're converting it, like when we were converting it from 1 year to 2 years.
Yes, I know. I'm saying that since I specifically am equating it for doing 1 year on one side and 1 year on the other, then yes, those numbers will be the same. But I didn't necessarily have to do this for 1 year. I could have said that 4 quarters gives me a year, and I could have adjusted these numbers in the exponents. For example, I could take the 4th root of both sides and have it cubed here in the first power here. I'm saying the reason why they're the same is because I'm doing it for 1 year on both sides.
No, I'm talking about
I know what you're talking about. It's the same reasoning. The reason why these numbers are the same is because I would be divided by a half.
Yeah.
There's 12 months in a year. There's 1 year.
Yeah.
There's a half of a 2 year period in a year. So they're both a half.
Oh,
It's because I'm specifically setting it equal to a year. If I did a different time frame, they wouldn't be the same.
okay.
So notice when I did it for this formula, I did the 2-year time frame. So this was double that because it was 2 years, and this was the 2-year rate, so it's just the first payment. But yes, that's why I said if you always go and equate things for a year, then yes, it will always be the same. Which is why I think about it that way. Think about it differently.
So if we're going about this one, we should compute the left side first.
Yep, compute the.
Take the 12 root, or take the 4th root.
I gotta get the d by itself, so I better take the 4th root, right? And then 4th root, flip it. And change size and multiply by 4. Anybody actually get that? This is one of those that's probably easier to do on the TI-30 than it is on the VA2 if you're doing exam FM. That's why I said you should take both calculators with you into the exam if you're planning on taking the exam. Some of them are just easier to type the stuff in on than others. You can do this with your VA2, but I would say you probably should get very versed with using your store functions. Your store and recall buttons on that calculator.
Can you even take the 4th root out of this thing?
Yes, hit your exponent button, y and the x, type in 4, and then hit the reciprocal key, load over x. That gives you 1/4 power. So then it equals. There's 4th root. You can do all these on the VA2 Plus. I'm just saying it's probably easier to do it on the TI-30. If there were no other reason, is you can see the things on the screen, right? Because the VA2 Plus, you're only going to get a number at a time that's on the screen. You can't see what you typed in. And if you think you did something wrong, you're going to have to go back and retype everything back in. Whereas the TI-30, I just go back and edit it. As we go along the semester, I will say more things about what I think can help you save time on the exams. It's a timed exam. If you're not going to take it, you can ignore all those tips. But, pardon me. Can I get this number?
I got C, and that's right.
If it's so 13.7%. Is okay? Pardon me. All right. See if we can do some other ones here. Let's look at, this is number 5 on the extra packet that I gave you last time. All right, number 5 says that you've got two payment streams that have the same present value. Payment stream 1 is 100 at time 0. Oops. It's 200 at time n, and it's 300 at time 2n. That's payment stream 1. Before I do anything else, let's talk a little bit about how we can get what the expression would look like for the present value of this payment stream. I need to move it back. I need to put everything at the same time. Since it's present value, I need to put everything at time 0 because that's present value. There's a difference between present value and current value. Current value is whatever time you're talking about. present value is always times 0. So it's asking about present value, and a lot of problems that you deal with either are present value or accumulated value. There are some that ask for values in the middle, but in general, it's present value and accumulated value. All right. We talked a little bit about time diagrams before. I think the time diagrams are more helpful later on when we start adding more payments in, doing annuities and stuff like that. But I'll start trying to introduce some of these time, because some students like the time diagrams. I can tell you that I did exam FM and I didn't draw a single time diagram with the entire exam. I'm an algebraist, pictures don't help. I don't do pictures. All right, but some people find it helpful. All right, so I don't have the exact times here, so that's why I just used the n and the 2 and I didn't bother putting a scale for the rest of it. Okay. But when you're drawing these time value diagrams, typically what you do is you put the payments at those various times. So we've got 100 at time 0, 200 at time n, 300 at time 2n. And we need to move all of these things back. All right. So this is a value at time n, and I need to move it backward to time 100. Okay? So that present value of 200 at time n, let's figure out how we would do that. Well, the present value is somewhere sitting over here. I don't know what that is. But what we're assuming is that if I accumulate it, if I accumulate it for n years, or to time n, I should get 200, right? The 200 is a future value. I'm trying to figure out what the present value is. Well, we can do that by dividing. So your present value would have to be 200 divided by 1 plus I to the n. Notice now that this looks like accumulated value times something that gives me present value. That's that discounting idea, right? And they actually use that same word here, even though I've got annual effective rate in it. They use the term discounting to talk about taking your accumulated value and moving it back to present value. It's called discounting. Okay? So that's used enough times that they use a special notation for this. Instead of writing 1 over 1 plus I all the time, they use a special letter, because of course they do. They have to add another symbol in there. Okay? So the symbol, you've probably already guessed it if you've read the problem. We would write that as v to the n, where your v equals 1 over 1 plus I. This is a formula that you're going to want to remember, because a lot of problems have v in it, and you're going to have to, but you're going to be given I, or vice versa. So this is definitely one of those first formulas that you should remember. And there's a bunch of them that go along with it, with v and d and I, and we'll talk about some of those in a minute. All right. So that's the present value of 200 at time n. So what about the present value for 300? Well, I got to take this 300, and I've got to move it all the way back to time 0. But using the same idea, the present value for the 300 is what? Using the same idea we just did for 200. Good. Yeah, we 300 v to the 2n. Good. Same principle, right? Hopefully it's obvious what the present value of 100 at time 0 is. It's going to be the 100, right? So now it asks for the present value of the payment stream, right? And I like to say things with payment streams. The present value of the payment stream. Well, we've got the present value now of 100, of the 200, of the 300. if I want the present value of the stream, what do you think I need to do with those three values? Add them together, yeah. We just need to add them together. So the present value of the stream, so the present value of this stream, and I'll call it stream 1 because that was the problem, the number that was given in the problem. The present value of stream 1 then will be 100 plus 200 v to the n plus 300 v to the 2n. All right, so this is the present value for the first part. What about the present value for the second part? The second part says what? 600 at time 10, right?
So at time 0, it's 0.
So at time 0, we don't have any payment, right? But we've got 10 here. We've got 600, and I need to move it times 0. So what's that present value going to be? E to the 10th. Good. Yeah, exactly. Does that make sense? All right. So that's the present value for stream 2. And this says that the present values of these two streams should be equal. So what do you think we should do with the two present values? Make them equal. So what we've created is what your book refers to as an equation of value. We'll set these two things equal to each other. And solve. Now your equation of value in this case was set for the present values. It's possible that you might set the cumulative values equal to 0. It might be equal to each other. You might set some value in the middle equal to each other, because it has to be equal to times 5. It's just, you're going to make the equation based on the problem saying it's equal at some time. That's all equation of value. I'm only mentioning it because of what the book says it's called. This makes sense, right? It says the present values are equal. What are you going to do? I'm going to set them equal, right? And the problem's telling you what to do. So say to find the present values, make them equal. Now, one of the reasons why I wanted to do this problem is, there's actually two reasons, but the main reason is that this is quadratic, right? This is v to the n and v to the n squared. Now, in this case, they give you what the value for v to the n is, correct? So just plug it in. In other cases, you might need to either factor or use the quadratic formula to solve for v to the n. So the main reason why I did this was so that you could see this quadratic form. It is very important that you remember the quadratic formula because it will come up. And they will not tell you to use the quadratic formula. And it will not be given to you. Okay? But it is entirely possible that either you'll need to factor or use the quadratic formula. Okay? This one you don't have to because they gave you the value for v to the n. I just want to mention that is something that to be aware of that you'll need to remember. Because of course you're going to remember a whole bunch of things. All right. But this one's not bad now, right? The problem asks us to find I, but we know v in terms of I, so the first thing we do is find v, correct? We know that our v to the n is 0.76. So in that second part, this is v to the n squared, so we'll have 0.76 squared here. Do the arithmetic on the left side, divide it by 600, take the 10th root. I'm going to skip a lot of arithmetic details because I'm going to assume you can do arithmetic, at least with the help of a calculator. Haley can, apparently. Anybody get what the value for v should be after doing that? This is another case, bless you, this is another case where I think the TI-30 is probably the easier calculator to use than the VA2. Not that you can't do it. Just saying I think it is easier. You see the value for me?
0.9662.
Okay. 0.9662. One thing I will definitely make sure to remind you.
66, not 2.
Oh, I thought you said 9622, sorry. 9662? Sorry, I just misheard. I wrote down what I heard, I didn't hear correctly. Okay, so remember that you're doing this for you, obviously, in the problems. So if you're writing things down as intermediate steps, that's perfectly fine that you write only a few decimal places. But make sure you keep the values stored in your calculator for rounding error purposes. Don't round to 2 decimal places in each step and just keep going, because you're going to compound the crap out of errors. Technical term. All right, so now the problem didn't ask for v, the problem asked for I, but we know a conversion from v to I, right? What was v again?
1 over 1 plus
1 over 1 plus I. So your I will be 1 over the 0.9662 minus 1.
0.03.
0.35? Okay.
So it's
3.5%. It's okay? We happy with that? All right. So, any questions on that at all before I talk about some of these other conversions? Or I'll just start talking to the conversions because, talk to myself. All right. So, remember that we also had the formula that 1 over 1 plus I was 1 minus D? Remember when we started doing discount? So that gives us another formula for your V equals 1 minus D, if you've got the effective discount rate. That's exciting. Or, let's see if we can do another one. So this one, if I go back over to the first equation over here, D is equal to 1 minus 1 over 1 plus I, or 1 minus V. But if you get a common denominator, you get I over 1 plus I, or IV. So there's another conversion formula. So there's several of these little properties that can pop up. If you look at one of the problems in the book, this 3.16, they give you a bunch of different ones and ask you which one's false. So just, I'm not going to write them all down, but they've got, one of them is I times 1 plus I gives you D over V minus VD. I squared is D squared over V squared. ID is equal to I minus D. That problem, 3.16, is a good one to go through and see if you can figure out which one's not right. It's a good one to go through. It reinforces the formulas. It's a good practice what to do. Hopefully it reinforces the formula. Like I said, though, there's going to be lots of different formulas, lots of different conversions. Some of the problems that are on exam FM like to give you the answers in terms of formulas rather than just numeric answers. So that it tells you how it wants to know that you know the formulas and can manipulate them. So that pops up as well. Let's do one more. Let's look at number 7 on page, or on the handout, sorry. Says $1,000, pardon me, $1,000 immediately and $1,500 at the end of the first year will accumulate to $2,600 at the end of the second year. Calculate I, where I is a nominal interest rate convertible semi-annually. Okay. So notice again that this problem is telling you how to figure out an equation to solve. If you like diagrams, let's think about the diagram. We've got 1,000 at time 1, or excuse me, time 0, 1,500 at time 2. Those are your investments that you're going to make, and you're supposed to get to an accumulated value of 2,600. If I remember the numbers correctly, because I didn't look back at it again. Now, I purposefully wrote that 2,600 higher than the other two, because you're not putting in 1,000 and putting in 1,500 and putting in 2,600, right? You're going to put in 1,000, put in 1,500, and take out 2,600. So there flows in different directions, right? All right, so you need to figure out where do you want this to be equated at. We need to figure out an equation. You need to figure out at what time do you want this equated. Now again, the two most popular are at the beginning or at the end. You can do the middle, but usually you think about equating present values or equating accumulated values. Okay. Me personally, I would probably do the accumulated value, because if the problem says $1,000 now, $1,500 in a year, gives me 26 and 2, right? So I would probably do accumulated values and set those equal, because the right-hand side, all I would need to write is equals 2,600, right? Do you agree with that? All right, so that means I want to take this 1,000, move it to time 2, this 1,500, and move it to time 2. I want to accumulate it, right? So to get $1,000 moved to time 2 with an interest rate convertible semi-annually, what should I multiply the 1,000 by? Okay, 1 plus I over 2, I'll write as I2 over 2 to the second power, right? Or is it to the second power? I think it's to the fourth power, right? Because I got to go 2 years, right? So this converts it to a semi-annual rate. This moves it 2 semi-annual periods, right? So it's I2 over 2 semi-annual rate for 4 semi-annual periods. How about the 1,500? Yeah, that one's a squared, right? Okay. Is okay? Everybody see why that's the equation that we want? Anybody want to see why that's the equation we want? Yes.
So the 1,000 is being interest taken on it for 4 periods, and the 1,500 is taken on it for 2 periods, and then those together make the final.
That's right. That's exactly right. Yep. All right, so this is what I was mentioning before about recognizing quadratic equations. This is another quadratic equation, right? In fact, what I would probably do, if it were me solving this, I would first write this as 1000x squared plus 1500x minus 2600 equals 0, where your x, right down here, where x is 1 plus I2 over 2 squared. Figure out x and then figure out I, instead of writing it all. I mean, you can write it all out at once, but I think I would make a substitution so I see the quadratic equation and then figure out the number. Of course, oh, hey, I'm out of time. Of course, you know from quadratic equations, how many solutions should you get?
2.
2. So probably only one of them is going to make sense. So usually what happens, like Nick said, you usually get one positive, one negative. So the negative one doesn't make any sense, obviously. For interest rates, sometimes you might get one that's bigger than 1 and one that's less than 1. And it'll tell you what the interest rate means less than 1, less than 100%. So see if you can finish that problem off for next time. And ask questions about it. And I think next period on Friday we'll have a problem. Right. Have a good one. We'll see you Friday or in about 7 minutes.